Our next session is on connectivity, where we have 3 insightful talks from Guam Exchange, ISOC, and AWS. I would like to begin by inviting Mr. Jose Santiago, as Senior Manager of Interconnection Strategy from Guam Exchange, who will share his insights on Guam's cables, data centers, and IXPs. Please join me in welcoming to the stage Jose Santiago.
All right. Good morning, everybody, or good afternoon, half a day. My name is Jose, representing Guam. Today I'm going to be talking about all the new infrastructure and everything we've been doing in Guam in the past couple of years, some updates, and how everything kind of fits in together. All right. So as they were saying, we're talking about the cables, data centers, and IXPs. And we're going to start off by talking about the current state of Guam, right? So right now, today, there are about 4 cable landing stations with several of these subsea cables coming through. But the problem is none of these intercept at any point, right? So a lot of the cables come in through one landing station, get power, and go on to the next destination they're going to. None of them have any interconnects. And if they would try to, it'd be very expensive. Although a lot of these landing stations have some carrier neutrality, it's just there's no dedicated point to carry them across the island, right? And another point is there's no IX in between any of these. So all of these cable landing stations are all dependent on cross connects. And the current state is all of these cable landing stations, they're not exactly data centers. They're just cable landing stations with retrofitted small spaces for data centers, not a dedicated, full capacity focused data center. And so that's what we're trying to do, right? So at Guam Exchange, a subsidiary of Citadel Pacific, we're building a dedicated data center to interconnect all of these cable landing stations coming through Guam. I'm sure you guys have seen all of those new information from Google in the past couple months, since like early this year, announcing all of their Pacific Connect program, where they're going to connect Guam to the rest of Asia Pacific, to the US, and integrating all of the Pacific islands in the region, right? And so we're going to use that Guam's as a hub, as a advantage, and connect all of those cable landing stations into one singular data center. And in that data center, we're going to create an added value of an IX. I'll cover that more. All right, so this is our proposition. With the new cables coming in from Bifrost, Echo, Apricot, and TPU in the next 2 years, coming up 2025, 2026, with an addition of a 5th landing station, right? You can see we're going to build a data center right in the middle, so it's all interconnecting, equidistant from each landing station. If you look at the landing stations, they're all across the shore. Being an island, we're susceptible to things like tidal waves or, environmental issues. We've put the data center inland in the center of Guam, about 33 meters above sea level, so no risk of any tsunamis or wave issues, water issues. And that way, and we're going to keep it open access. We're going to be having fiber directly connected to each landing station at the start. Right now, these landing stations don't have interconnect, but using this facility, we'll have interconnect straight away to each landing station. So if you were to come in through any of these landing stations, you would be able to order a cross connect to any other subsea cable through our data center. Right, so this is phase 1. We're going to call it Harmon 1, and you'll see why we call it Harmon 1 in a second. At Harmon 1, we're going to have a 260 rack capacity, about 1.3 megawatts. Every part of the facility will be a N+1 configuration, meaning we'll have 3 generators, 3 UPSs. Actually, we have 12 crack units supporting all of the cooling for this data center. So it's pretty exciting. Today is May 30. We are going to go live with our new data center on June 30. So exactly 30 days from today, we'll be ready for service with a data center and an IX. Okay? These are just all the technical features of the data center, as you would expect from any data center, 24/7 monitoring and access and all those things. Pretty standard in what you would call a tier 3 data center today. Right, so I was mentioning why it's Harmon 1, our phase 2, Harmon 2. We're gonna build Guam's first data center campus, not just a dedicated data center, we're gonna build a data center campus on this island. Right, we're gonna capitalize on creating Guam as a regional hub for Asia Pacific, and we're gonna establish as much resiliency as we can. Last year, 2023, Guam got hit really, really hard with a super typhoon, Typhoon Mawar. So establishing Guam as a regional hub for connectivity in this area, we're gonna establish a second data center so that ensures continuation of business for people who co-locate with us, right? We're gonna have a modular design, even more rack space. I have an elevated situation over here. And one of our key features or benefits of our data centers that our parent company also owns a gas company. So therefore, we will be customer number one when it comes to fuel delivery. So we'll be able to keep everything running as much as possible. Right? So that's phase 2. All right, and then I mentioned we're also gonna create a brand new IX. So on Guam, there's currently 2 other IXs, one dedicated for regional academic resources, and the other one called Marix that I helped build in the past couple years. But this one is gonna be a little bit different, and it's gonna have more reach because of that cable landing station leverage. Right? So just to start off, this is what we're going to start off with an 800 gig throughput switch. There's some of the technical features. We're going vendor agnostic, just using whatever's best and available. We're not being choosy or being particular, but those are some of the equipment that we're going to be using. At the start, we're going to have 10 gig ports and 100 gig ports available at our IX. Okay. All right, so earlier in the slide, we saw that we had a lot of west landing stations, but in the idea of resiliency and redundancy, we're gonna start looking at landing cables on the east side of the island, right? So we're gonna start creating fiber rings all around the island and making sure that we have capacity east, west, and redundant routes. So if there were ever any problems with a tidal wave from the west, we'll have protection from the east, right? We're really looking at our landscape of the island and making sure that we're covering all bases. So we're looking at landing some cable landing stations here in the east. And that's not it. So if you guys know Guam and its region, the Marianas Islands, we have some neighboring islands. So this is one of them. It's called Tinian. We're going to build another landing station in Tinian, right? So it's not just all focused on Guam. We're gonna build the Marianas region as a data center, fiber capacity hub thing. And in this one, we're going to try something new. We're going to go for a 6 to 18 megawatt solar powered data center, right? So going green, trying some efficiency, so that our carbon footprint in the midst of all of this data growth is sustainable. So we're keeping in mind a lot of resiliency, redundancy, and sustainability when we're building our data centers. That way, we can have future growth without impacting the local economy too much. Being an island in the Pacific, we should utilize all the resources that we can. I won't be surprised if we start looking into hydroelectric power from using the waves in our beaches. Okay. So that's pretty much what's happening in Guam since I've been on board, and a lot of the activity we've been doing for the past 2 years. With direct partnerships with all these cable operators. So that's it. That's Guam for now. Thank you.
Thank you very much, Jose, for sharing with us the dynamics of having a data center on an island in the middle of the Pacific Ocean. Would anybody have any questions before we move on? Excellent. So let's continue on the topic of connectivity with our next presenter, Mr. Naveed Haq, who is the Asia Pacific Regional Director for Infrastructure and Connectivity at ISOC. His talk today is on Southeast Asia's internet resilience. Please help me give a very warm welcome to Naveed.
Hello. Swadikap. Good afternoon, everyone. So yeah, Naveed Haq from Internet Society. I'm the Regional Director for Infrastructure and Connectivity. And the previous speaker from Guam was talking about resiliency. So my discussion is also about resiliency. But before I go further, I want to ask, what does resiliency means to you? So if anyone wants to just very simply tell us what is the resiliency, what does comes to mind? Please. Very nice. Yeah, that's more of a user translation, but spot on. The ability of a network to maintain a minimum level or acceptable level of service, if I may say, in case of a disruption. So if something happens to your network, what is your ability to keep your service at an acceptable level? And those disruptions could be internal factors that hit your operations, or external factors just like tsunami or undersea cable cut, etc., etc. So we're going to talk about this resiliency in Southeast Asia, and for that I have this platform that we call Pulse from Internet Society, which is more of a data dashboard, a platform which curates data. So just to share that Pulse is not generating data by itself, but rather what it does, it curates data from various data sources to present it to the user in a way which is more readable and more useful as well. These are our data partners. You can see we have a very long list and a strong list of our partners, and while I'll be delivering my presentation, I'll be stressing more about increasing such kind of measurements and generating such kind of data on a more local basis, because data, as is the power. It helps you to decide and see what is happening, and perhaps put strategy around the future. And remember, our topic is about resiliency today. The platform in a nutshell talks about all of these things. It talks about shutdowns, it talks about technologies, it talks about concentration, it talks about resilience, and it talks about the country reports, which are more of a report that gives you an insight of a particular country. Today we will cover resilience and country reports only, because if we start from shutdown, and it will take a lot of time. But just for your interest, when you visit Pulse, you can navigate through all of these 5 various data points. Before I go into the resiliency, let's see what has happened recently and what we can learn from the recent incident. So in March, there was a big outage in West Africa. Some of you might recall that. It was all over the news, it was on Twitter. Internet was almost down throughout the west of Africa due to undersea cable cuts. And one of the key takeaway that came between the technical community is that you cannot assume resilience. So you cannot just assume it that we are resilient. There's a lot of things that have to be done, and some of the other key takeaways was particularly from the community groups like NOGs and peering forums and IXPs, how they help to maintain that minimum acceptable level of service in West Africa, and that perhaps give up an extra stress towards the function and importance of internet exchange point in keeping the traffic local and keeping it live. The second thing that happened was in Bangladesh with the CMV5 outage recently. And in that as well, we see a kind of a similar lesson, that the local IX, which is the Bangladesh BDIX, help to maintain the local traffic still going on. So people were still able to use a minimum level of service because of BDIX that kept the internet running in some way. And second thing is the local content. So of course you have an IX, you have the CDNs or those big names which have their servers in an IX and the service is still going on, so you don't feel much. But apart from them, another important aspect in Bangladesh case was that there was a high percentage of local content, whether it's the services, it's the websites, etc., available at the BDIX, not being hosted outside the Bangladesh, so which also kept the minimum level of service going on. Now let's come to the Southeast Asia. Yeah, but before that, when we talk about the resilience and the Pulse platform that I mentioned earlier, our platform actually defines the resilience as in the index, as an index which is around a set of 30 data metrics around infrastructure, performance, security, and market readiness. So these are the 4 key pillars based on which the Pulse platform generates the Internet Resilience Index for a region, globally, and also to an extent of a country. This is the map which shows you kind of a fair idea of the resilience based on, again, the data that we collect from all the partners and curated. And you can see the APAC, Asia Pacific, is between 30 to 55%. That is kind of an idea or a prediction or a presentation of how the resilience based on the previous 4 factors, the performance, security, infrastructure, and market readiness looks like. Overall, Europe as a region leads with the 60%, then Asia, then the Latin Americas and America, Oceania, and Africa. Again, based on those 4 factors. Overall, if we try to divide Asia as we do usually in terms of sub-regions, the Southeast Asia, where we are today, leads the rest of the Asia, together with the eastern part of Asia, which is of course Japan, Korea, China, and Hong Kong. And the Central Asia, which is the STANs, most of the landlocked countries, as they are still struggling, or the other way I can say is that they need to do more work to increase their resilience. Now let's dive down further into Southeast Asia, which is all the ASEAN economies plus Timor-Leste. You see Singapore leads, then we have Vietnam, Brunei, Malaysia, Thailand. So interestingly, Brunei, Malaysia, and Thailand somehow are at the same 51%. So that makes Thailand as among the top 3 economies in Southeast Asia. Again, based on the data that we curate on Pulse, which is of course an excellent news. And Timor-Leste is at the bottom. So remember those 4 pillars: infrastructure, performance, security, and market readiness. So this gives you a more detailed insight into those 20 data sets and what is the score for Thailand. We can see that security and performance, these are the 2 top perform pillars for Thailand. And if I go further, in fact, these red are kind of those areas which needs more improvement. And these blue one are the areas where the Thailand is performing very well. That includes data center, number of IXPs in enabling infrastructure, traffic localization, the market structure, and the route hygiene, in particularly from the security perspective, which is again good to see that Thailand, the routing security is taking up as a practice by the networks to make sure that the route hygiene is maintained. This is kind of a snapshot of our past 5 years of the growth of IXPs, which again depicts that Southeast Asia is becoming a traffic hub for overall Asia markets as well. So we see a lot of Indonesia, Singapore, Malaysia, Thailand, getting into this growth of IXPs. And then if you see the growth of data center as well, it's something where we see Singapore, Indonesia, Malaysia, Thailand, Philippines, and Vietnam. But and another interesting correlation that we saw is that the more connected economy is, the more data center you will see in that market. So it's kind of a direct correlation that how strong is your connectivity infrastructure in a country to attract investments for data center. And that's really amazing. Here we see the connectivity factor of various, again, economies. See that Cambodia, Myanmar, Timor-Leste, of course, they are kind of economies that need more work, and they are progressing. But at the same time, we'd really like to commend Cambodia, Laos, and Myanmar from the perspective of route hygiene. We see that these economies in Southeast Asia are kind of developing or underdeveloped, and they need more work, and they are, trying to, get more progressive in terms of connectivity and data center. But from the route hygiene perspective, really want to commend the efforts of the community, the NOGs, the IX in these three countries, Laos, Myanmar, and Cambodia, on maintaining a very high level of route hygiene, even higher than some of the other economies like Indonesia and Malaysia, and in fact even Thailand. You might know about MANNERS, which is the mutually agreed norms on routing security, a program that Internet Society started 6 to 7 years ago. And I see faces here. Archie is there, the back from Philippines, one of the strong advocates that we have for MANNERS. Recently, the operational side of MANNERS has been given to another organization, which is called GCA, Global Cyber Alliance. So please do get in touch with us or them if you want to learn more about the MANNERS and the routing security, or if you want to organize trainings, you want to have more understanding of it, please do reach out to me. But just to give you an update about MANNERS, that recently Internet Society has made a transition of its operational work to another organization. Now let's come to traffic localization. Again, Cambodia, Laos, Myanmar, even Philippines is kind of trying to get to that average threshold of 32% in Asia. But that's something that we are working to make kind of that 50-50 thing, where we can have at least minimum of 50% traffic localized within an economy, and we're working with some of the economies. If you want to know more about that, or if you want to work with us about that 50-50 traffic localization work, please do reach to me. Peering efficiency. So, this all is again a wealth of data. I will like you to please go yourself to the Pulse platform and explore, and if you have any questions, please reach out to me. But let's quickly go to the country reports of the whole Southeast Asia. Starting from Cambodia, we have Cambodia regional rank as number 15. The average regional rank for network assigned, the ASNs, is 25. So one of the countries that is progressing, but there are some of the data that you can see, which I was having a chat with the friend from Cambodia IX about, how there is a need to attract more investment and strengthen the local infrastructure inside Cambodia. Philippines regional rank is 10, and it's about the peering. Network assigned regional rank is 13. Internet exchange point regional rank is 5. Kind of a country which has made a lot of progress and is keep on making progress because of people like Archie. I would say, of course, this guy is one of the key guy you're going to meet from Philippines if you want to talk about these things. Thailand regional rank 7. So Thailand, of course, as I said, has made a lot of progress. There's still some of the areas which need more development, and forums like today are those forums where we bring all of the various mindsets to talk about what could be done and how we can collaborate. As we know, peering is all about collaboration, but there are other factors as well which come into the peering ecosystem: data centers, infrastructure, connectivity. So it's really good that Thailand has made a lot of progress, but still, there is still one more leap to be taken. as far as this the infrastructure is concerned in Thailand. Vietnam, so, you know, as I said, you go to the platform, you download the reports, and there's a lot of details available. I don't want to make you more bored. I think I've kind of made my point, and in terms of result. But what are the limitations? So this is something that I want to share about our platform. So the data is pulled from external public sources. So it may happen that it's not all time up to date. In terms of the Pulse platform. Within in-country measurement, it's difficult to validate data, and that's the point I really want to stress in my next slides. That perhaps this is the time when the local community, the peering forums, the NOGs, and other communities sit down and talk about how they can perhaps work toward in-country measurements. You know, there are a lot of things already happen. We know about the probes from Atlas and other probes which are available, and people are already doing measurement, but perhaps this is time to have this as a topic of discussion and see, you know, how the in-country data or the measurements could be increased to kind of have a more validated and more accurate data, which of course, as I said, is a power to make your decisions towards the future growth of infrastructure of connectivity in a country. And yes, of course, we all have a role to play. Key takeaways, again, I'm going to stress on a more insightful national measurements. Please do outreach to me. We have a project called Measurement, which is custodian of this platform as well. If you want to talk more about, if you're interested to join hands with Internet Society to kind of have those in-country measurements, we'll be more than happy to talk and help you where we can. Do subscribe to the newsletter, because this Pulse platform, we have recently started a newsletter, so you get those monthly measurement reports if you are kind of into data and that kind of thing. And you can review our Pulse RI, which is the Internet Resilience Index methodology as well, because we, of course, would like to further improve this methodology, make it more trusted, and for that, we need your feedback on how we can improve it. I guess this is my last slide. Thank you so much, and I'll be more than happy to take any questions.
Thank you very much, Naveed. Any questions from the floor? Okay. Thank you for
so much.
sharing with us. Thank you, Naveed. Let's continue on a topic of connectivity with one more presentation from Fredrik Korsback, who will be with us through video call. Fredrik is a senior infrastructure business developer at AWS. His talk today is on the deep dive on AWS Edge networking infrastructure. Please welcome virtually, Fredrik.
Hi, I hope you can hear me just fine. You also see my screen?
On behalf of the audience, yes, we can see you perfectly.
Oh, perfect. Okay, all right, perfect. Yeah. So yeah, I'm joining remotely. My name is Fredrik Korsback. I'm a senior infrastructure business developer with AWS. My typical key responsibility or area of responsibility is Northern Europe. But here I'm today talking with you about our net, like what we're doing in the networking space and a little bit about the innovations we're doing. There we go. Yeah, so to kind of start off the presentation, we need to look at maps. Like every network presentation contains maps, right? And to build a story here, we'll need to start with our cloud regions. Our cloud regions are, we have 31 today, and we have 5 coming soon. We just announced another one a month ago or so in Saudi Arabia. These are quite large builds. These are something that take years typically to build. They are very large. They are typically where we go and buy, for example, real estate and then take on a 15 to 25 year investment to build our own data centers and to fill them up with computers, right? So that's where the network starts. Something that we also added lately is local zones. And I think this is a product that you could call it the mini cloud if you want to, but they're not that mini anymore. I think the first one we launched in Los Angeles, I think we sold it out in like 7 days or something like that. So basically, every local zone that we have built since then, we had to grow quite significantly, either by building it larger or building more of them in the same area. So today, this slide is probably a bit outdated because I did it in November. So this says we have 21 available. I think the last number is like 28, and we announced like 4 to 5 more. And this is where the network expands, right? Really the networking requirements for these local zones are no different than the large cloud regions because they are effectively the same thing. It's just a size play, really. So that has put a lot of interesting challenges in our network for sure. To add on this, we had CloudFront POPs. They're available in Thailand, for example, and in many other locations. And the CloudFront is our CDN POP. CDN works best when it goes as close to the customers as possible. So they effectively we need to blanket the map to some extent. It says 450 here. This is also outdated because it's like, half a year old. So I think we're up to almost 500 or 550 or something like that. CloudFront POPs already. And this is a network, or rather a customer to our network that is growing extremely quickly. We will be adding 50 to 100 per year for the next 3 to 4 years, it seems. We also have an embedded offering that is not even counted on this POP page, but that is something that we put inside IXPs network. So to tie it all together, there is a lot of dots on this map all across the globe, and all the areas that are not currently have a dot in them, we probably have a plan for that. And to tie it all together, we have a network. Today, every single POP that we have is connected to our backbone. Our backbone is typically conformed out of 400 gig links. Today, we're in 245 countries and territories. And yeah, we connect all local zones, edge locations, cloud regions. Everything is connected in one big network. So you could say that we operate a little bit like a hybrid model. Like some CDNs, they build, for example, islands, like that every POP is an island. We have a model where every POP is connected to the backbone, but sometimes the CDN can function a little bit as an island. So what is new then? Or rather, what is cool? Because yeah, it's like, sure, it's one of the largest networks in the world, but what are we doing about it? So to start it off, we need to talk about custom software and custom hardware, because that is the end result of what I'm going to talk about. In AWS, we have something called tenets, where we decide on like the guiding goals of what we're trying to do. And in this case, we have that simplicity scales. The simpler you can make something, the easier it is to make it bigger. We also have an idea that we only focus on the benefits, that we kind of take our viewpoints and our the history aside and just focus just like what is actually delivering quality for customers. And also with this customer software hardware approach, we can examine all trade-offs. Like, for example, maybe we can consider that we don't need certain protocols that we would typically use in a network. Like, do we really need multicast? And if we don't, why do we even have that in our operating system? Just an example. So the foundational building block of our whole network today is based upon this device. It's a 32 by 400 gig switch. It consists of a single chip on a device that has the forwarding capabilities of 12.8 terabits per second. This is a quite common data center product, as you would see. It is available to the market. Like, sure, we've been building this for now 3-4 years, but it is really not a very exotic product these days. I think anyone could probably buy this type of switch and get it in 4 weeks for actually not a lot of money. So to look at the device, we were able to find a color that were not taken or not patented. So this lime green color, it was actually free to use, which is great. Because as I said, we operate with simplicity here, right? So we actually have color-coded switches depending on where they need to go or what they are supposed to do. So in the board network, we have 2 flavors. We have this green one and we have another purple one, which I will show you later. So really what I want to show with this picture, right, that this is, it's a fairly simple device. This doesn't look very impressive. If you ever open a router or switch or anything like this, this probably looks like any of them. Like this might as well be a 10 gig switch from 3Com, right? But the only, I guess, a little bit cool thing with this is the red part here at the top. So this is the actual computer, right, inside the switch. But I guess the cool thing here is that this is actually on a Graviton 3 controller. So Graviton 3 is AWS own CPU. It's an ARM-based CPU that we manufacture ourselves together with our ODM teams. And we have built in a lot of cool things into this. So this is actually a pretty powerful computer because this means that we can do a lot of things on the switch which others cannot because this is actually a pretty powerful device. So really that's the only thing that would set this apart from any other type of white box or whatever you can call those type of devices, right? And to productify this, we certainly need more than one. So when we go build this, this is our smallest like total building block. So when I want to deploy a new country, for example, it's like I want to launch, I don't know, Thailand is a good example of that. This is the only thing I can order. Like I can order one or multiple of these effectively. And it is a claw type of network design, which means that we have leaf and spines. So the switches here in the top is the T1 devices or the leaf devices. This is where we will connect peers, we will connect backbone, we will connect basically anything that is a consumer of the network. And then this row here in the back, or these T2 devices, they're all the spine switches. So what we end up with here is that we will have 1,024 400 gig ports. We will use half of them just for interconnect. So we will use 256 of them at the leaf layer, 256 at the spine layer, just by interconnect, which gives us 256 400 gig ports for clients. These clients could come on 400 gig, of course, but since we are, I guess, a little bit ahead of the curve on the 400 gig deployments, that means we obviously also support 100 gig. And the way we support 100 gig is by putting in a 100 gig optic in a 400 gig slot. We also have a possibility for certain peers to do 2 by 100 gig optics in one 400 gig port to save a little bit of money for us, right? And that's also the reason why, for example, 10 gig is not very, it's not something that we could do very easily, or rather not at all actually. Because to produce 10 gigs in this configuration, we need to put a QSFP plus adapter, or rather 40 gig QSFP plus adapter in a 400 gig slot and put in a 10 gig SFP. So we will be down speeding from 400 gig to 10 gig to produce 10 gigs. So that's not really something we'd like to do. Anyway, this whole thing is a 30 kV rack. That is not always available for sure. So we also have a version where we split this over 4 racks. The good thing here is now we come down to 9 kVA racks, which is typically available in most data centers, I say. The bad thing here is that we cannot use duct cables anymore, which brings up the cost and most importantly the power consumption quite a lot. So obviously we do not prefer to build it like this, but if the data center only supports this type of build, we will do this. So this is a 100 terabit router, but divided over 4 racks. Yeah, this is the same picture, right? We do 32 by 32 by 400 gig port in this case. This is a picture, so the blue ones are actually our demo equipment. They're not green, they're the same thing as the green switch, but this is when we bring them to trade shows and stuff like that. If we need to scale up, right? Like if you count it well enough, you realize that one single rack, it has 256 ports for clients, it's 512 for internal leaf spine connections, and 256 was unused. And the reason why those are unused is because the only way to scale this is to scale it vertically, right? So we can add more racks to enable more capacity. And with our current chipset, so the current 12.8 terabit chipset, we can go up to 32 racks. And this means a 3.2 petabit router. Luckily, we have not needed to build an edge pop with this type of capacity yet, but we're quite close in Ashburn to actually needing this in one single location. The good thing here is that hopefully the silicon evolution catches up Because if we can go to the next generation of silicon, which means a 25.6 terabit chip, or even further with the 800 gig networking, we will be on a 51.2 terabit chip. And that could actually bring us to having this type of capacity, but with 1/4 the amount of racks, which obviously is good for everyone, because that saves a lot of money, power, and everything else. Right. So from architecture point of view, this is what we end up with, right? We have 16 spines, 16 leads, and we can support 256 pairs basically on one of these devices. We obviously do lags and all that kind of stuff to aggregate that. And yeah, if we need to go wider, we go wider. The whole fabric in itself is non-blocking, right? So that's why we have 50 tera in the interconnects, in the internal interconnect, to make sure that we can never be congested internally inside the fabric. So some of the challenges that we have, like the first challenge, it might seem like a simple one, but it took us almost a year of delay to actually sort it out. Was DAC cables. So if you ever worked with a DAC cable, maybe you ever worked with 40 gig DACs or maybe 100 gig DAC, you know that they are, if you make them 2.5 meters, they are quite stiff. Like on 400 gig, the outer diameter is 11 millimeters of cable, right? And that's a pretty stiff, that's like a garden hose almost, right? So that's a pretty stiff cable. And when you need to cram 256 of these in a rack, just as the picture shows here to the right, you actually don't get any air through. So you have heating and cooling problem, but you also have like fairly rudimentary operational problems. Like you cannot extract the cable from a port. Like how do you get your hands in there to get port number 37 out? That is actually really hard. So we played around with like really long pull tabs, and we played around with special tools and these kind of things, but in reality we were not successful. So what we had to do was use something called an active DAC, which has retimers in it, and really everything with that is bad. Like it is much more expensive because it's like half the component cost of the whole thing is just the retimers, and it is drawing a lot more power because those retimers need power. Otherwise, a DAC cable is extremely power efficient, and at scale it matters if the DAC cable consumes 0.5 watt or 5 watt, right? Like the difference there at scale is enormous, right? Like that could be the, I don't know, the power consumption of a small country, right? But we had no other way, right? So we had to go up to these more expensive, more fancy cables, but we could reduce the outer diameter with like half if we used that type of cables. And I guess a common question here could be like, well, use optical instead. Well, the thing is with optical, for these short distances, it's that the latency is higher because you do another digital analog conversion. It's also much more expensive, and it consumes at least twice the amount of power as these already power-hungry active DAC cables. And compared to passive DACs, that's 15 times the power consumption of like AOC or any short-range optical would consume a lot more power. So we ended up with this one. But we can only support about 2.5 meters, right? So if we need to do this build where we have 4 different racks, then we need to go optical anyway. So speaking about optical, this is an actual picture of our typical patch racks, right? So we have about every 5th rack or so has to be only patch cables. And one way of actually fixing that or making that better is to think about how we handle breakouts. So the optics you have here on the left is a fairly standardized breakout cable where it is ending up in 4 LC connectors from one single optic. Because obviously this 400 gig build, we're going to use a lot of breakouts for clients because the CDN servers or the backbone transponders or whatever we have is more likely going to be 100 gig than it is going to be 400 gig. At least when we started to build this network 2-3 years ago, the majority of our consumers were 100 gig. So another innovation that we did, or rather that we did together with our vendors, was to try to avoid these patch racks, or rather to try to avoid these breakout racks. And we, together with the company called Senko, invested the patents and everything on a connector called SN. And the idea with this is that inside a QSFP-DD form factor, which you can see to the right, it's a 400 gig DR4 plus optic. You can actually fit all 4 pigtails directly into the optic. And this means we can avoid these breakout tracks, and instead be able to first not only troubleshoot, but also just to take away possible intersection points where we could see faults coming in. Because these when you run a large scale like MPO based breakout networks, you actually realize how much churn on the problems you have there. Like cleaning those type of things is not very fun, and finding which one of those panels actually is broken is not that easy. So with this, we could actually troubleshoot individual clients as well. Like imagine if we have servers here on the other side. Like every server we have is 100 gig or up today. So here we can troubleshoot each individual server without taking down the other 3. So this is the type of thing that we use internally. This is not for peering, because this is short range. This is 2 kilometer and less type of optic style. But for everything internally, this is actually a pretty nice success story, I would say. It's something I would encourage people to look at if you think that you're going to have a large breakout network. That is pretty nice with being able to individually troubleshoot everything. Right, so the thing that we have now is the small number of rack variations when I started 5 years ago, we had a lot of rack variations. We had almost every site was artificially or was artisanally created, right? Like that we tailored every site exactly to what it needed. Now, we really only have 3 different rack variations when we go and build a new site. Like we have either the 30 kV rack, or we have the version with 10 kV rack, which means 4 racks, and we also have a version with DWDM in. And that's really everything, right? Everything comes pre-cabled from our ODM. So the rack here to the right is effectively how it's loaded on the truck. So everything that is supposed to be inside the rack will already be inside the rack. So we built this in the factory. We ship it out. We ship it without software, because this means we can use regular shipping companies. We don't need secure or that type of shipping. We can use regular shipping, because what we do is that all these devices support like a little craft terminal or whatever you want to call it, where we just collect the inventory of everything that's installed into the rack, and we compare it with the bill of materials, right? So it's like, oh, do we have 256 DAC cables? Do we have 32 devices? Do we have the management switch? Do we have all of these? And when all of these matches and adds up, and the right inventory numbers, etc., is all there, then we can ship in our own software to kind of make this thing go when they're inside our data centers, right? That's actually a pretty neat solution to solve otherwise a pretty complicated problem about shipping around intellectual property without a lot of insurance and a lot of legal involvement. So to finish this off, I promised to talk about the purple box, and I will do that. And it is actually the same exact hardware as we talked about earlier, the green switch. But this is dedicated to do DWDM interconnect. And the idea here is that, yeah, it is a router or switch, whatever you want to call it, it's the same thing. It is not really a Max Bonder that you would buy from regular vendors. This is a switch with DWDM capabilities. So we filled this. So as you see here, the hole to the left here, they look a bit different. They have a lot more cooling holes, or these speed holes around them. And what we do is that we fill these with 400 gig ZR optics. It could be ZR plus, it could be bright, it could be whatever, depending on which reach we need. And to the right here, we will use the DAC cables to kind of connect it back to the spine fabric. And with this, we end up with a possibility to build like high scale DWDM for almost no cost, or at least very low cost compared to what it usually costs. And the only difference here, why this is a larger switch, is because of cooling. The DWDM optic shown above, which is a 400 gig ZR, consumes 5 to 10 times the amount of power as a regular like LR optic or whatever you have, and we just need to get cooling into the box. The other only difference between this and the green switch is that we also have MACsec integrated into the switch. There's another chip that does MACsec on all ports. Because the idea from AWS that every single link that leaves our data center, like it could even be if it goes from one POP to another, let's say in Thailand, if we have 2 POPs, if those POPs are not in the same cage, we will use MACsec in between. So everything that we do not have control over the fiber will have MACsec. So of course this device also is integrated with MACsec. And unfortunately, they're not purple in this picture, but it is the silver box, a pre-production build. Well, this is how it looks like when we order it from our OEM, right? So it comes pre-connected with the duct cables back to the spine switches, and then we fill these up to the left with how many DWDM optics we need. And that enables us to build pretty effective metro edge POPs. Where we can scale capacity really quickly if we need to. Okay, a little bit on the architecture and software. So of course, automation is everything. Today, I don't think we have any humans touching anything in the network anymore. We're quite far from that. Our network engineers, they are more comfortable working in a Git-style repo than they are working in your traditional like Cisco iOS type of config. We write network config as code. That's the short reality, I guess. We have auto remediation on most things. Like we look at DMP logs, we look at syslog, we look at all the logs and try to fix problems before they happen, or rather, we try to fix it automatically if they happen. One way of doing this is by taking devices effectively out of service. Like if we detect something is bad, we will most likely route away almost immediately. And when we are safe in that sense, we will look at what was actually the problem. Like if it starts to drop, if our systems see, for example, buffer overruns or it's memory errors, for example, the first thing it will do is it will drain the device and it will send it to a human if it's not able to solve it itself, and then we'll take a look at it from that. We also have something called deployment coordination where we, we never try to, when we upgrade, for example, this router is actually 32 devices. And obviously we upgrade them sequentially, right? We don't take everything down immediately. So we have many stages of how we think about the coordination, right? It's like, oh, we don't do this POP, but at the same time we do this POP. And inside this POP, we only do this device if this device is up, right? So there is a quite complicated matrix of how this thing should work to make sure that we are never take anything down that we cannot route around, right? That's also why you would see, for example, the AWS peering people, such as me and such as Yukiko, which is responsible for Thailand, and some of our others, would typically prefer to do a lot of interconnect, right? So that we spread it over many devices. Like in any given POP, as you can understand, we have at least 16 edge routers. And in most occasions, we have more than that. So we typically prefer to spread the capacity out to achieve as much resiliency and as much ways of sending traffic as possible. So the way that we look at this, right, is that we start from the network ASIC. That is one component. And on top of this, there is an SDK because we're actually multi-sourced on the ASICs. There's not only one ASIC, it's many vendors of ASICs. And we integrate towards this ASIC through a unified SDK. And on top of this SDK, we have a Linux kernel, of course. And inside this Linux kernel, we have our software stack, right? So we have the management plane, we have the routing protocols, and we have the telemetry, which I guess is the three most important thing to be able to build a router. So we have been looking at the idea of a router as more of a Lego type of thing and not a vertically integrated solution. Like we can actually replace each layer here individually and work with each layer here individually without much problems actually. So the telemetry team, they only need to work with like what do the kernel do? Like what can we do from a kernel perspective? And SDK, they only need to work with ASIC and then present it up to the kernel, etc. So yeah, that is a pretty pragmatic way of looking at how to build a router. Like we think, or rather we know, that we think about routing, building routers and switches the way that any regular vendor would do, because that's really the only way to do it correctly. So the last bit here is to look at disaggregated control plane. Today, when you peer with us on this new style of device, you will actually not peer with that actual physical box, the green box that I showed you before. You will actually peer with the local cloud. So it is a container-based thing where every router gets their own container. So in a default setting, we will spin up 32 containers, and each one belonging to each one of these routers, right? And the good thing with this is that we can throw hardware at the problem much faster than what is otherwise possible if you run a traditional vertically integrated router, right? Like here, if we see that, for example, oh, router number 4, it has a lot of peers with like high amount of churn, you can just give that box more memory or give that box more CPU, like without anyone noticing, right? And this means we can achieve faster convergence at a much higher scale than would otherwise be possible. And in some occasions, you know, maybe a whole device or a whole router, so let's say router number 7, in some metros, we have peers that are large enough to consume all of the ports on one of those devices in a single leg. Like, I don't know, like a big US operator in Chicago or Ashburn. It is not unusual that we have 2-3 terabit lags with a single ISP, right? And that means that this ISP, they effectively get a whole BGP container off the road because there's no other peer at that box. And the good thing here is that, you know, we can iterate this quite quickly. Like if we need new functions, we can get them almost immediately, right? Because we don't need to take much consideration into the hardware running, because that's a separate thing. Like we can, if we need more hardware, which effectively means we need more bandwidth, we change the hardware, but we keep the software and the BGP stayed intact. Or if we need more features, like I've been working quite a lot with ArcAPI and everything we're doing around that, both now and in the future. I don't really need to pay attention to what's happening on the router because we do everything in this container-based solution. And from the peers' perspective, they don't really see anything different. The only thing that people sometimes notices is that before the BGP session is up, if you try to ping, you actually get a duplicated package because both the router and the container will answer on BGP. But other than that, this is about 70% of our network, or I think, or the goal is 70% of our network is migrated to this solution by the end of this year. And today, I believe we have about 56% is fully migrated to this solution, which I think is pretty cool. I'm at about time, yeah, 3 minutes to go. You can email me any questions if you want, and I guess we have time for 1 or 2 questions if anyone has them.
Thank you very much, Fredrik. Any questions from the floor? 1 question.
Awesome.
Hi everyone, I'm Nan from BKNX, and first of all, thank you very much, Fredrik, for give us a wonderful presentation, and I hope you can join us personally next time.
Sure.
So you, in your presentation, we see you mentioned 2-tier cross connection. So I wonder how you differentiate between the local tier and between global tier, how it connect to each other.
Oh, you mean how we would connect 2 POPs to each other, or what do you mean?
Yeah, exactly. So do you have the SPI connect together between the global so on?
No, not really. I mean, these leaf devices, right? They also function as backbone routers, effectively, right? So these client ports could also go to other POPs or to other sites, right? And that's also why it looks crazy, like it's a crazy amount of bandwidth here. But this includes all clients, right? This includes, you know, transit peering and backbone. So that's why we need to build this pretty big, typically always. So we would connect them on the leaf layer.
Thank you very much.
Thank you very much. Any other questions? Okay, thank you very much, Fredrik, once again for sharing with us how to dive deep into networking infrastructure.
Sounds good. I will come to Thailand someday and we can talk more about it.
You're in Sweden now, right?
Yes, I'm in Sweden, so I'm gonna have my morning coffee.
Excellent. Good morning to you over there. We're gonna have lunch now, so thank you. Take care.
All right.
Bye-bye.
Good one. Bye-bye.
Thank you very much, all participants and guests, for a very fruitful morning today, and I hope you worked up a little appetite as it's now time for our networking lunch. As such, we have prepared lunch for you at the LG floor, which is at the plate room at LG floor. So don't forget to bring your lunch coupon with you to enter the dining room. And once again, don't forget to stop by Bang Pan, that's bangpan.thai in Thai spelling, or bangpan.in.th in English spelling. And if you have already registered, be sure to pick up your iconic products from our local communities, or register now and get rewarded too. So please have a nice lunch, enjoy some shopping, enjoy networking, and may I ask everyone to return to this room again at 2 p.m. where we will begin our afternoon session. Thank you. Bon appetit.